Higher life.
All right. The discovery of the motor cortex has a special place in the history of systems neuroscience. It was almost 150 years ago that Edward Heitze and Gustav Fritsch first demonstrated in the dog that low current stimulation of the anterior lobes in one hemisphere produces movements on the opposite side of the body. Stimulation in other parts of the cortex produced no movement. But specifically within this excitable area, which exact movements were produced depended on the precise location of the stimulating electrodes. These results were presented as clear evidence for the theory of cortical localization, the idea that different parts of cortex are dedicated to different specialized functions. But it also suggested that motor cortex may play a role in the direct control of movement and not just in perception or cognition. But there was also a dilemma that was best pointed out by the German physiologist Friedrich Goltz. He argued that in the dog, it is impossible to completely abolish the movement in any muscle or destroy any perception by localized lesion to any part of the cortex, so localization theory must be wrong. At the historical International Medical Congress held in London in 1881, he faced off against David Ferrier, a rising neurologist who is using stimulation to produce the first functional maps of the cortex in primates. At this conference, they each presented live lesion animals for public examination. From Goltz, a dog with large bilateral lesions to the frontal and parietal lobes was seen to freely move around and avoid obstacles. On the other hand, Ferrier presented a monkey with severe movement impairments to the right arm and leg following complete removal of the left motor cortex. At the end of the conference, the animals were killed and their brains inspected. The lesions in Goltz's dog were smaller than anticipated, while Ferrier's lesions were extensive and included damage to sections of subcortical white matter. In the end, the striking image of Ferrier's paralyzed monkey helped him claim victory for the theory of cortical localization. The dilemma, however, remained. Why do we see such large differences in the relative strengths of the impairments following motor cortical lesion in primates versus non-primate mammals? Some insight was obtained from studying the corticospinal tract, the direct monosynaptic projection originating from layer 5 pyramidal neurons in the motor cortex to the spinal cord. These neurons stretch their apical dendrites all the way up to layer 1, which is what allows surface stimulation to be effective. In the monkey, if you completely section only this pathway, you get long-term movement impairments in the ability of animals to control individual finger movements, such as is required in order to grab food effectively from tiny holes. However, it also leaves many other behaviors intact, such as the ability to walk or climb. In other species, comparable deficits have been reported, but they are very subtle, requiring ever more elaborate assays in order to even reveal an impairment in movement at all. There is one anatomical specialization that may help to partially explain these differences. In the monkey, the corticospinal system densely targets the ventral motor neuron pools in the spinal cord. But this is not accurately recapitulated in most other mammals, where the corticospinal targets are mostly restricted to spinal interneurons in the intermediate zone. But also the corticospinal system is not the only output from the motor cortex. And indeed, the motor cortex projects to practically every other area involved in the control of movement. If the role of the corticospinal tract is the control of fine movements of distal extremities, then we can ask, what is then the role of all these other projections? And also, what do all these areas contribute themselves to movement? It has been known for a long time that in cats and dogs, the basic pattern of stepping during locomotion can be sustained by spinal cord circuits alone. and indeed can be initiated by direct stimulation of brainstem circuits. And indeed, as you can see in this video, a fully disturbed cat can even switch the controller to adapt to changes in external conditions, such as in this case, the speed of the belt. So if subcortical systems can already do so much for the control of movement, what can we say is exactly the role of motor cortex? Our experiment started in the same spirit as these cat locomotion studies, by looking at animals with and without motor cortex moving across a stable obstacle course. All sessions were run in the dark, and there were infrared illumination. When we tested bilateral abutanic acid lesions to the forelimb motor cortex in rats, we observed that there was no obvious difference in lesion versus sham performance moving across a stable obstacle course. In fact, we even extended these lesions to parietal cortex in order to cover all areas that have been reported to have monosynaptic projections to the spinal cord. For these lesions, we used more invasive methods, such as aspiration, which are also known to cause damage to subcortical structures. But even in these animals, despite an obvious initial impairment in the placement of the paws in the initial trials moving across the obstacles, they were all able ultimately to surprisingly fast adapt their behavior and achieve good performance moving across the obstacles. Across these two groups of lesions, and compared to controls, we found no difference in learning performance, as measured in the average time to cross the obstacles in each daily session. All animals were able to adapt their performance and started to move efficiently in less than a week. In the extended lesions, we did find a slight reduction in the accuracy of paw placement, as measured by the average number of slips per full crossing. However, interestingly, this deficit was limited to the hind limbs, with no obvious impairment in the placement of the forepaws. This may be comparable to the reported deficits in fine movements from full corticospinal lesions, but it obviously had no effect in their overall crossing performance. So we wondered what would happen if we then challenged these animals across more challenging environments. By permanently making some of the steps in the course, or even all of them, free to rotate. Interestingly, both lesions and controls were found to have no problems dealing with a configuration where the center two steps were made unstable. And indeed, even for the most challenging configurations, where we make all the active steps free to rotate, we found that all animals managed to find some way to move effectively across the obstacles. Some animals were more skilled than others, but if you look across the group, this difference in skill was found to have no relationship to the presence or absence of motor cortex. And indeed, overall, we again found no difference in their performance moving across all these different conditions. So at this point, we were intrigued by how well these animals were able to handle the challenge, to the point of gracefully jumping around, freely spinning obstacles, hundreds of trials in just 30 minutes. How does the role for the motor cortex in the direct control of movement fit into all of this? One different and very interesting idea has been presented in a series of studies looking at cats moving in more challenging conditions, such as stepping over the obstacles. They have shown that activity in single neurons in the motor cortex is dramatically increased when the cat needs to modify its step to move across the obstacle. And interestingly, in a way that is not directly related to just the changes in muscle activation as the animal is moving. So the fundamental suggestion here was that motor cortex perhaps does not need to take direct control over subcortical systems. And perhaps it might just be increasing the capacity of them, working together with brainstem and spinal cord, intervening only when necessary. So what exactly is this additional capacity that motor cortex may be adding? When is it necessary? How can we test? How can we test the necessity of motor cortex in these kinds of challenges? It was here where we decided that we needed to expand the space of possible tasks. We needed to find some challenge for these animals that would really reveal that what motor cortex really brings to the game. And this was out of this necessity that we created the modular box for composing hardware and fast and create behavior assays, and the bonsai framework for rapidly composing reactive software. So the shuttling assay that I was showing previously and that I will discuss in the rest of the talk, I think is a good example of how we put the modular box to good use. So now I will just take a few moments to demonstrate bonsai. So environments, and in fact most data acquisition systems, need sensors. And in bonsai you can just access these sensors directly, like this. So the video capture device will allow me access to the raw stream of images coming from this camera that I have right here. But in order to create an interactive environment, we do not need to access just the sensors. We need also to process the data from these sensors and use it to generate some kind of response in real time. So since today we were playing with so many videos, I thought it would be fun to create an interactive movie player from scratch that I could use to control, or I could control the precise playback of the video by the movement of my hand. So here's how you would do it in bonsai. So I need some way to segment my hand. So I will do it by just the difference in brightness. Then I will threshold, where I will segment the objects in the thresholded image, compute the statistical moments, take the largest of them, and just add a quick condition to check that we actually have an object by basically testing whether the area of the largest object is greater than 0. So this tells me I now have an object segmented, which I will test. So we need to adapt the parameters to the current conditions of the room. I'll look for dark objects. This is good enough. Just one more filter to make sure only big objects come through. And I should have my largest object being followed on the image. So now what I need is the video, which I will add with a file capture. This is the video I want to show you. I will first show you the video running at normal speed. So this is an animal moving across a challenging condition, very fast. Now I want to reveal to you exactly what the strategy that he's using to move this fast in detail. So what I will do now is create my index into this video out of the biggest object. So I will take the center of mass, the x position of the center of mass of the object, and normalize it to fit between 0 and 1. And then I will store all the frames of the video into an array, combine it with my index, and basically now write a little expression to index that array. So I will index the array with my number from 0 to 1 times the length of that array. And because this is a floating point number, so I need to cast it into an integer. And if this works, then I should have my video in control of my hand, which now I can use to show you what actually is happening, that as he moves across the assay, if you notice the position of the, so he's stepping with his front step on this step, As he continues stepping, he rotates the step such as to make a stable platform for the back paws to hit on. And he does this continuously. And that's how he can move so fast across a completely unstable obstacle course. So this is just a simple example, but hopefully it can give you some ideas of the kind of things you can do with this framework. But for now, let's go back to our exploration of behavior. So using these tools, we made our obstacle course reconfigurable on a trial-by-trial basis by using a dynamic lock system with servo motors placed on the back of the assay, which allows the individual steps to be made stable or unstable. We took care when designing this system to make all the modifications covertly, such that the animals running in the dark do not know which step, the state of the step, of each step, until they actually walk over them. So with this assay, we can test animals now in a variety of conditions, where the change in the step can be made unexpectedly or can even be uncertain. Using computer vision, we can track the position of the animal's nose or other features of the animal's behavior, such as the activity of the paws on each step. Using these features, we analyze in detail the posture with which the animals approach the obstacles. We had noticed that when the state of the obstacles changes permanently to unstable, the animals adopted a different posture when approaching the steps, with a lower center of gravity, keeping their snouts close to the step as if in preparation for the movement. If we now track the tip of the animal's nose as he hits the step, and plotted the progression over trials, then you can see that this adaptation actually develops quite quickly after a change in stability. Another way to summarize this data is to just plot it in X and Y in a scatter plot, colored by the condition of the steps in the two conditions. And if we now group all the animals, including controls and lesions, then you see that actually both groups of animals can actually do this adaptation. So again, we found no difference in their behavior. We then looked into the remaining condition, where the state of the steps is now uncertain, fully uncertain. So this is done by basically shuffling the state of the center steps following a uniform distribution. So basically in each trial, the state of the two center steps is either both stable or both unstable. So the first thing we wanted to make sure is that there was no cue in the environment that might inadvertently be telling them what the state of the world is. So what we did here, we plotted the position of the nose of the animal divided by the conditions whether the current trial is stable or unstable. And you can see there is no difference. So there is no significant difference. So basically this told us that the animals really don't know what state this step is in the current trial, at least as is revealed in their behavior. However, if we now group the same data, not by whether the current trial is stable or unstable, but by whether the previous trials were stable or unstable, then a subtle but significant difference is revealed, suggesting to us that these animals might actually be adapting dynamically their posture to their expectations about the state of the world. But surprisingly, again, both controls and lesions were able to do this dynamic modification. So this to us was really intriguing, because it told us that motor cortex, not only can you move without a motor cortex, but you can even adapt your behavior to changes in the conditions, even when the state is uncertain. However, in all these conditions, there was ample time for animals to adapt to the dynamics of the world. They have some days of training. So we wondered what would happen. What happened in the first time that the environment changed from stable to unstable, where you basically have no time to prepare. It's a completely unexpected change. This moment is unique. where we went back and looked in detail into the behavior of each animal in this first collapse, during this first collapse of the steps. And we essentially found three types of responses. The first one was investigation, where the animals immediately direct their attention to the manipulated step and actively engage and manipulate it. The second response we called compensation, in which the animals switch their strategy in order to deal with the perturbation. So this is not just a slight adjustment in the ongoing pattern. It is a complete change in the controller strategy, which engages all the musculature of the animal in order to clear a potentially dangerous obstacle. The third response we called halting, in which the animal neither compensates nor investigates the steps. It simply stops his ongoing movement. So strikingly, when we compare the behavior of lesions and control animals during this first collapse of the steps, we observed a surprising bias towards the halting response from the animals with lesions to the motor cortex. So to summarize this data across all animals, we plotted an ethogram aligned on the moment of first contact with the steps and sorting the lesions by their lesion size. And you can see that in controls, there is a clear preference for either the compensation or investigation responses immediately following first contact with the step. Whereas on the lesions, there is a clear bias towards a halting response. And interestingly, on the smaller lesions in our group, there already started to appear again the compensations that we observed in control animals. So in order to further confirm this trend, we also looked at our extended cortical lesions during this first collapse of the steps. And again, we found that most animals also seem to show this halting response. But interestingly, in some animals, we also observed another behavior, which we had never seen before, which is basically ignoring the change of the steps during many trials. Until at some point, they ultimately do notice, like in this case. But if you go look in detail at what exactly was the reason of the change, you notice it's as if they require a stronger stimulus in order to something in their brain to switch and notice that something has changed. So it is ironic that after all these different tests and conditions that we subjected these animals to, the most striking difference would come down to a few seconds in a single trial. It is only in this critical moment that missing a motor cortex seems to matter the most. In roughly half a second where you live or die by how much your actions fit in your environment. What does this mean? So there is a tendency to associate fast corrective responses to lower level automatic reflex systems, and precision, deliberation, and planning to higher level cognitive systems. But how much does precision really require cognition? And on the other hand, how much can a fast response tell us about our cognitive understanding of the world? I would like to illustrate these two different views with a few examples. So in automation and robotics, precision and fine movements are absolutely not the issue. For a long time, industrial robots have relied on active feedback in order to blow past the human speed accuracy trade-off in specific motor tasks. Once the control problem and the parameter space is precisely defined, and you have good enough sensors and actuators, then the controller is able to reliably execute any movement, no matter how complex, over and over again. So what exactly are the hard motor control problems that robots still cannot handle, but that we clearly recognize as a hallmark of mammalian and indeed human ingenuity? So this is what we really mean by dexterity. while dozing off in a couch without much room for movement. But suddenly something in the movement of the baby that he knows is behind him brings up an image. She's falling, what can I do right now with my motor system? This is mammalian dexterity, saving the day in the nick of time in a daring attempt to prevent the worst. What makes this movement so different from any other movement is context. The understanding of where you are, how the world works, of what you can do. It was recognizing this important motor problem and how well mammals deal with it that led us to the crux of this thesis, the proposal that the primordial role of motor cortex is exactly the generation of this kind of robust responses. So what comes next? In the first attempt to take a look at the physiology of motor cortex, during such conditions, in a small group of animals, we implanted flexible surface electrode grids in motor and somatosensory cortex in one hemisphere. These grids allow us to record field potentials over a large area of the brain and correlate individual signals not just with behavior, but with many other electrodes. To conclude, I would just like to share with you some preliminary data, some preliminary results from our ongoing analysis of this data set. So when we tried to reconstruct neural activity during normal locomotion in a permanently stable condition, we observed a very consistent evoked response from the frontal regions of the grid when the animal stepped with a contralateral paw on an obstacle in a permanently stable condition. So this is very similar to the kind of phase locked responses that you get in cats stepping on a treadmill. We were now interested to see what these responses would look like when the animal confronted an unexpected perturbation. So in order that we could record for more than one trial, we had to adjust our behavior protocol slightly. So now, instead of changing permanently the state of the step from stable to unstable, we did it infrequently, so once every 20 trials. So this gives us not many more trials, but around 10 in 200 that the animal will do. But when we did it and recorded what the signals look like, we found a much larger response in the motor cortex, with a surprisingly large signal to noise given the number of trials in the anterior regions of the grid, specifically when the trial was unstable. And on those same sessions, on the remaining stable trials, we found again the evoked response that we had observed in the permanently stable condition. So this might be for many reasons, so we wondered maybe this is related to some kind of large compensation movement the animal is doing during these trials. So we looked into our video, synchronized video, in order to look for clues. And if you look at the movement of the animal until the first peak of the negativity, there is no obvious motor response from the animal by that time. So this suggested to us that this is not just a reflection of what the animal is doing. So we observed the same basic phenomenology across all the three animals that we recorded, but there is clearly still much more work to do in order to digest and fully interpret this data set. However, we found it very encouraging that even the very first early results already seem to indicate an involvement of these structures during the behavioral conditions for which we found motor cortex to be necessary for. So in the future, we would like to understand more about the neural bases of these robust responses. This will ultimately require better behavior assays in which we emphasize the ability of animals to deal with unexpected conditions. But it will also require significant improvements to our ability to record brain activity simultaneously from multiple areas during these unique situations. Because if we are pushed into situations where we only have a few trials in which the structure that we care about is really engaged, we will need to extract the most information that we can during these situations. So that is all for now. And in terms of acknowledgement, it's very complicated because I have been here for a while, and has been a really transformative experience for me. I am a totally different person now, and many of you, if not all of you, had a big part in making this happen. I highlighted some people, but really, I don't know, it's impossible to fit all of you in one slide. There's a little picture here, including all the CNP. There were so many stories, so many things. I couldn't summarize it. So thank you, all of you, really, for helping me along this path. And of course, thank you all, for the members of the jury, to also coming and accepting the invitation to be here.